All right, so with Lewis structures, these are actually some really nice ways that we can represent some chemical compounds. We use these because it helps to analyze patterns of behavior, and that we can really harness the power of these chemicals. The definition of Lewis structures, these are diagrams that represent an atom arrangement and bonding in covalent compounds, right? Specifically covalent compounds, which are compounds comprised of non-metals. Okay, so a couple things before I move on. One, I'm going to look at a periodic table. You're going to find a periodic table really helpful here. You also should have at some point this Pauling scale of electronegativity, which we'll use to help us out. So make sure you keep these handy. But let's go and deal with the first part. Remember, this is your blank periodic table. Your nonmetals, they're kind of either on the left side of this sort of imaginary zigzag line, or they're to the right. And if you remember, the nonmetals are, of course, to the right. The one exception, of course, is our friend hydrogen, which is his own little princess. So that's always going to be something you have to remember about the number or the identities of these metals and nonmetals terms. The first one here, a pair of electrons shared between two atoms. So I'm going to go ahead and give you some alternatives, and there's one that we'll use the most. But the first one is that you might just hear a bonding pair of electrons or bonding pair. Sometimes you'll just hear a single bond. This is probably the easiest way to identify it. So bonding pair or single bond. You can also hear sometimes like a single covalent bond. Really, single bond is most likely the one you'll see. Second one here, a pair of electrons not involved in bonding. Okay, again, giving you two alternatives, but one will be used more often than the other. First one would be non-bonding pair. Makes kind of a little bit of sense there, right? These are not involved in bonding. But also you might see these as lone pairs. Right? Lone pairs of electrons, which seems kind of oxymoronic, right? But you get the idea. Two bonding pairs between two atoms. Well, if one bonding pair is called a single bond, two bonding pairs might be called a double bond. And then finally, three bonding pairs. Surprise, this one would be called a triple bond. So single bond, lone pairs, double bond, and triple bond. These are ones that we'll use quite a bit to describe these structures that we draw. The next thing we need to define is our valence electrons. Now, we've defined valence electrons in several ways up to this point, but the easiest thing that we're going to do is to identify them as the valence electrons of an atom are the outermost electrons. The quickest method of determining the number of valence electrons of an atom is by the group number that the element is in on the periodic table. Specifically, it's the numbering that involves the Roman numerals and that letter A. For example, an element in group 3A, right, group 3A has 3 valence electrons. An element in group IVA, IV meaning 6, so group 6A has 6 valence electrons. That's simple. If you remember from one of your old periodic tables that you marked up, this thing has it all written in there, right? Because if you remember at the top, you have two ways of numbering your groups, 1, 2, 3, 4, all the way across. But then you also have this other one, sort of secondary one, where it's 1A, 2A, kind of skipping all of these in the middle, 3A, 4A, 5A, up to 8A. All right. Now, let's go back to the notes here where we look at how this works. Now, this process that I'm going to outline here is super important that we follow more or less to a T. It is something that will help you remain constant and consistent as you work on these, because otherwise it can kind of get a little iffy. So let's talk through this. First of all, the process. Number 1, find the total number of valence electrons for all atoms involved. We'll talk about what that means in just a minute. But mostly, again, looking at the valence electrons like we just said, find them on the periodic table, count them up. 2, arrange the elements so that the least electronegative element is in the center. Now, why do we talk about having that Pauling scale pulled up? This guy right here? Well, because that's why this is how we can know our electronegativity, right? So it's the Pauling scale of electronegativity values. So basically, we find the individual values on here, and then we just see which one's the least and put that in the middle. Now, you'll find that with the exception, there's one exception, is that hydrogen, this one's always going to be on the outside, never in the center. So even though hydrogen may sometimes be the least electronegative element, we just put it on the outside always and forever. Okay, next step, number 3. Draw one covalent bond, which looks like just a line, between the center atom and each of the outer atoms. Each covalent bond represents 2 electrons. If you remember, that's a shared pair of electrons. And then B, calculate the number of remaining electrons. add remaining electrons, if there are any, to the outer atoms as lone pairs to satisfy the octet rule. Now, the octet rule basically says that based on its arrangement, we have to see whether or not an atom has 8 valence electrons, right? 8 assigned electrons at least. Okay, octet, right? Oct representing the number 8. And then we calculate the number of remaining electrons again. So we have multiple steps here where we have to figure out what's left over. Step number 5, add remaining electrons to the central atom to satisfy the octet rule. If your central atom does not have the octet, you can then use lone pairs on outer atoms to then form double and triple bonds. Notice how, again, in this whole process, the only time you really start seeing double and triple bonds is at the end. There's a tendency to want to try to add double and triple bonds at the beginning. Y'all, you gotta wait till the end. It's going to be the most consistent way to do this. Finally, this one's, again, kind of a rare, not rare, but this is a lesser seen but still important example. Sometimes we'll work with ions that look like compounds, right? There are a bunch of groups of things that make up an ion. We'll get to some examples later on. But just to have this down, these ions will require a set of square brackets looks kind of like this, right? Square brackets, and the overall charge on the structure. Okay, now, again, we're talking very, very loosely. Like, this is a process where it's kind of hard to see it without an example. So, hey, what do you know? We have some examples here. Now, these, again, I'm going to go through slowly to make sure that we walk through the whole process. The one thing that you need to do, all right, the one thing you need to always do at the very end is to always double check that your octet rule is satisfied. And we're going to do that with each of these examples. Let's start with part A, CH4. Our friend CH4, this one, we're going to start off by looking at the total number of valence electrons. All right, so let's go back to the periodic table. Let's look at our valence electrons for carbon. All right, carbon is right there. Carbon is in group 4A, so it has 4 valence electrons. Put that out. Hydrogen. Well, hydrogen is in group, let's try this again, 1A. So in group 1A, it's going to have 1, but then there's 4 atoms of hydrogen in the molecule, so we multiply that by 4. So we have 4 plus 1 times 4. So that gives you a total of 8 valence electrons to work with. Now, that's step 1. Step 2, arrange the elements so that the least electronegative element's in the center. All right, so we can look at carbon and hydrogen, and you can look at the Pauling scale here. So let's go ahead and find that guy. Hydrogen is a 2.20. Carbon is 2.55. So the rule says the least electronegative elements, that'd be hydrogen. But we just saw that a minute ago. Hydrogen is always going to be on the outside. So even though it has less electronegativity, we put hydrogen on the outside, and therefore carbon goes in the middle. So we sketch it out, we do C, and then we kind of arrange it so that you have it like one C in the middle, and then a bunch of H's kind of evenly distributed throughout around the C. Step number 3. Draw one covalent bond between the center atom and each of the outer atoms. Here we go. So I'm going to go ahead and draw a single line connecting that, and that. One thing you shouldn't really expect to do, I'm going to do this kind of in a blue line right here. You should never really expect to connect a bunch of these on the outside. That rarely ever happens in very, very specific examples. But for now, we just know that this is going to be our structure, the way it's drawn. Then we have to calculate the number of remaining electrons, knowing that each covalent bond represents 2 electrons. All right, so we know that we've assigned 2, 4, 6, 8 electrons, right? Because again, each bond represents 2 electrons. So that's 8 electrons assigned. Therefore, we don't have any more electrons assigned. Are we done? Unfortunately, no, we're not done. Because the one thing we have to do is we have to double check the octet rule. That's kind of like an unspoken 8th step here. Right? Check octet. That says octet, O-C-T-E-T. So that's kind of these unspoken rules that anytime you do this, you want to make sure that you did it correctly. And one of the great ways to do so is to double check that octet rule. So let's see how this works. I'm going to use my carbon here in the middle. And basically right now, what's assigned to it? Right now you have this bond, this bond, this bond, and this bond. So these 4 bonds together are all assigned to the carbon. So altogether, those are actually, again, going to be 8 that's assigned to carbon. Does it satisfy the octet rule where you have 8 assigned electrons? Absolutely. So carbon, good, thumbs up. What about hydrogen? Well, hydrogen's out here, and it only has this 1 bond attached to it. So how many electrons are assigned to hydrogen? Only 2. Right now, again, kind of have to take a little, not liberties, but the term octet isn't literally applicable here, but the idea is still valid. Does hydrogen have the appropriate number of electrons assigned to it? Turns out, yes, hydrogen ends up being an exception, which we'll look at later on, but hydrogen, again, having 2, we're good. So if you look at the other ones, H also having 2, good. H having 2, good. H having 2, we're set. So altogether, we are now comfortable saying, yep, this guy is drawn correctly. All right, what about the next one, NH3? All right, so let's walk through the process one more time. So N, this one, how many valence electrons does it have? Looking at the periodic table, this guy is going to have nitrogen. It's going to be in group 5A, so it's going to have 5 valence electrons. And hydrogens, we did that earlier, since they're each 1, but there's 3 of them, turns out we're going to have a total of 8 valence electrons. Okay, then we add them up to get 8 to now assign. Let's go ahead and write this out to where nitrogen is going to be, or excuse me, the next step here where you take the elements and write it so that the least electronegative element is in the center. All right, so which one is that going to be? Well, it turns out, just based on the numbers, hydrogen is less electronegative, but like we said in the previous example, it's an exception. Hydrogen is always on the outside, so let's go ahead and draw. So nitrogen is on the inside. That's our central atom. Okay, oops, I think I skipped a little bit here. Let's try that again. So you draw it where N is in the middle, you have H's all around it. Step number 3, draw one covalent bond between each of the atoms. So N to H, N to H, N to H. Now we can go draw those in. If we know that each bond represents 2 electrons, how many electrons have been assigned at this point? We've assigned 6 electrons at this point. So that means we have 2 left over, right? We have 8 to start with, we assigned 6, 2 left over. So with those 2, it says in step number 4, add remaining electrons to the outer atoms as lone pairs to satisfy the octet rule. All right, so let's go ahead and look at the outer atoms. We have hydrogen, hydrogen, hydrogen. We're not really going to add a lone pair here, right? I'm not going to do this because, well, hydrogen, we kind of been looking ahead. We know that hydrogen's good with 2 electrons, so it wouldn't make any sense to try to add more electrons right here. So actually, I'm going to avoid doing that for any of these hydrogens. Instead, you look at the next step. Right? Since I can't assign any, we still have those 2 remaining electrons left. So then it says add remaining electrons to the central atom. Right? So then our central atom here is nitrogen. It's in the middle. So go ahead and add that lone pair electron in the middle. Therefore, we have now assigned all electrons. All right, let's go ahead and double check your octet rule. Your octet rule for nitrogen, right? This guy in the middle, you have bond, bond, bond. That's a total of 6, right? 2 plus 2 plus 2, that's 6. And then you have this 2 right here, and then 8. That's octet rule, good. Hydrogen, we said earlier, because it has 2 electrons on it, it's good also. This whole molecule, the way it's drawn, check plus. All right, let's try the other 2 here. So hydrogen and oxygen combining to make water. Let's do this process where hydrogen is actually going to be 1. There's 2 of them, and we're going to add that to the 6 valence electrons of oxygen. Again, looking on the periodic table for that, that's 8 valence electrons. Let's go through the process. Step 2, drawing it out so the least electronegative element's in the middle. Well, it turns out hydrogen, again, still can't be in the middle, so let's do it. Oops, excuse me. So let's do it where we have H, O, and then H. So O is in the middle. We draw a line between each of them, so line and then line. That represents 4 assigned electrons, so we have 4 electrons remaining. Step number 4, add remaining electrons to outer atoms. Well, these outer atoms can't really accept them, so we're not going to do it there. We still have 4 remaining electrons. Step number 5, add remaining electrons to the central atom, and then we have that. All right, so we have octet rule satisfied. We have 1, 2, 3, 4, 5, 6, 7, 8 electrons assigned to oxygen. Good. Hydrogens, each of them have 2. We're good. 8 total valence electrons. We are all set. Check plus. Done. Finally, CH2O. All right, walk through the process. C ends up having 4. Hydrogens total is 2, right? Again, individually 1. I just don't feel like writing that out. But oxygen is 6. That's a total of 12 valence electrons there. Now this one's going to be a little bit trickier because you have 3 elements to consider, but one thing you can go ahead and eliminate is the fact that hydrogen is always going to be on the outside, so that's not going to be in the middle. So then it comes down to either carbon or oxygen. Which one of these is more or less electronegative? We've got to look at the list of our Pauling values. Let's go ahead and take a look. Oxygen here, carbon here, or you might remember from the trends that oxygen is more electronegative, and so we go ahead and put carbon in the middle. So the least electronegative element in the center, carbon, and then we have our other elements drawn around it. We got H, H, and then O. That's step 2. Step 3 now. Draw one line between each of them. Line, line, line. each of them representing 2 electrons. We go ahead and count how many remaining are left. We have 6 assigned, therefore we have 6 remaining. Let's go ahead and go to number 4, add remaining electrons to the outer atoms as lone pairs to satisfy the octet rule. So if you look again, we got to assign 6 to an outer atom. This outer atom and this outer atom, these hydrogens won't accept it. But look at the oxygen. Oxygen 8. What do you know? We have oxygen that can accept some electrons right now. Make that more obvious. Those are the 3 lone pairs there. At this point, we don't have any more electrons left to assign, so let me redraw this so it's a little more clear. We don't have any more electrons left to assign, so at this point we can kind of pause, but we're not quite done. Because again, one of the unspoken rules is that at this point, right, we have to double check your octet rule for everything. If you look, hydrogen good, oxygen also good, right? 2, 4, 6, and then you have that pair that makes 8. What's the problem with carbon? Carbon only has 2, 4, 6 assigned to it, and of course it needs to have its octet rule satisfied to get 8. How do we do that? Let's look at number 6 right here. If the central atom does not have an octet, you use the lone pairs on an outer atom to form double or triple bonds as necessary. All right, so what do you see here? This oxygen, you have a couple lone pairs. Again, I don't have any lone pairs on hydrogen as an outer atom, so let's go ahead and take this pair right here, and we're going to move that down there. Right, so to kind of show you that process, right, that's the step that occurred. You have C, double bond O. These two are untouched, H, H. And let's see what happened. We have 2, 4, 6, 8, right, assigned to oxygen. 2, 4, 6, and 8 assigned to carbon. All right, we're all set. And one last thing, again, never be shy about this, is to go ahead and double check that you assigned the right number of electrons. This when we started with 12 valence electrons, your final structure should also have 12 valence electrons. So 2, 4, 6, 8, 10, 12. Good, we're all set. So CH2O, check, we are done. Last little bit here, we got a couple of exceptions. Some atoms need fewer than 8 electrons. That's going to be hydrogen, which only needs 2 electrons to satisfy the octet rule. Lithium only needs 2 to satisfy its octet rule. Beryllium needs 4, and boron needs 6 valence electrons to satisfy the octet rule. All right, in case you're wondering why those, well, again, if you look over here back at a periodic table, we have hydrogen, which we mentioned earlier. Lithium, which is in the same group as hydrogen, so it'll behave similarly. It only needs 2 valence electrons. Beryllium is the next one that needs 4. Boron is the next one that needs 6. And back to carbon now, which we know needs 8. Finally, over here, some p block elements in period 3 and greater. These elements have empty d orbitals that may engage in bonding and allow for something called an expanded octet, or up to 12 may surround the central atom. So we'll get to that later, but I wanted to point out 1 or 2 things. Again, we're talking about period 3 and greater. So if you look at a periodic table, right, we're talking about period 1, 2, 3. Actually, let me look at the other one. It's already marked up. Period 1, 2, 3 and greater. So that means this one and physically located below on the periodic table, not above. That's not what it means by greater. And the other part is this, right? Talking about p block elements. So we're talking about the p block elements, which are over here on the right side. Right? Any of these will be able to have the expanded octet. And then finally, it does talk about having some expanded octets where up to 12. So if we normally have 8 for our octet, we can have up to 12. So that means you could potentially have either 10 or, again, up to 12 valence electrons around that central atom. Okay, that'll do it.